Okay, let's continue. Okay, so now we know like okay, n divided by 3 is sufficient, but can we get even lower than n divided by 3? Okay, so so 3 coloring I already explained. Okay, so starting from root or any node, okay, you just do the 3 coloring, and yeah, since there's no cycle, so you don't need to worry about having trouble. I mean, using just 3 colors. Okay, so so the next question is it possible to reduce even to like I mean further than n divided by 3? Okay, so here we try to create a case that we have to have roughly n divided by 3 cameras. Okay, you can see this is like a prong, 梳子啦. Okay, this shape looks like a prong, like you have a lot of like this small angle, okay, on top of this, and assuming you have many of these, so you can imagine, okay, basically, okay, you need to have you need to install a camera at the top of this point, right? Top of this triangle. So the number of this top of the triangle will be roughly n divided by 3, right? Because well we have 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. You can see the top of triangle is roughly n divided by 3, right? Okay, you may need one extra camera to cover these places at the bottom, right? So roughly n divided by 3. Okay, so you need, I mean, for this particular situation, obviously, okay, we need at least this many cameras, right? So which tells you, okay, n divided by 3, okay, a number of camera, okay, for a simple polygon with n vertices, okay, n divided by 3 floor cameras are occasionally necessary. Occasionally, why is occasionally necessary? Because we have a worst case here, right? Okay, and and always sufficient to have every point in the polygon visible from at least one of the cameras. Okay? So it is sufficient because we have proved by 3 coloring that n divided by 3 flow is sufficient. But in some worst case, okay, we do need this many cameras. But other than those situations, okay, we may have even lower number of camera. Okay, consider the convex polygon. Okay, we just need one camera. We just need one camera at maybe one vertex. That'll be good enough if it's convex shape. Okay, because remember, camera can rotate, right? So I mean, in that case, like one camera is enough. But so n divided by 3 is always sufficient, and occasionally necessary. Okay. So let's finish the discussion of the number of cameras. So we have discussed like how many cameras are necessary, but we haven't really talked about the algorithm to triangulate. Okay, we haven't talked about the algorithm to triangulate the simple polygon. Not yet. Okay, so so now, okay, let's consider how, because previously we just assumed we already done the triangulations, okay, but now let's consider how we do this triangulation, okay. So the previous, remember, like in our proof is more of like because we are using like induction, right? We are using induction, but that induction process can actually turn into an algorithm. Okay, basically, we use the leftmost vertex, right, and try to find the neighboring vertex, and try to draw a line and see if it intersects with any other edges, right? If it is, we try to find the vertex that is leftmost in that triangle, right? So basically, okay, each time, okay, after going through all this process, you will be able to introduce one diagonal line, right? You will be able to introduce one diagonal line. So how much time does it take? Because you need to check for every side, okay, if in the neighboring, okay. One moment. Okay, so okay, remember you find the leftmost vertex and you consider this this diagonal, and then you try to check this diagonal with all the other sides, right? All the other sides. Check if this one intersect with this, and so on. Okay, so you need to do this n-2 checking, right? Right, and then okay, after that, you if there are some intersections, then okay, you try to find like the leftmost one. Okay, I mean, and you draw a diagonal there, right? Okay, once you are able to find some intersection, okay, then I think that in terms of computation, you can see that obviously this n-2 checking, linear time checking, is more expensive than this situation, right? Because this situation, we only have a few points that need to be considered, right? Okay, you don't need to consider all the vertex in here. Just maybe just a few vertex here that has intersect. Okay, their side has intersection with this one. So really like in terms of like this introduce one diagonal, it needs this much computation, right? Linear time, right? To introduce one diagonal, right? One diagonal. But how many diagonals do we need?
-3.
Yeah, I mean roughly, order of n, right? So the total, the kind complexity will be big O n squared, It is because like you know, if you need this much time for one diagonal, eventually you just need n squared amount of time to you know to get like the triangulation process done. Okay, so. Vertex with their coordinate. Draw the vertex with their coordinate.
If we sort the vertex with their coordinate before we find all the diagonals.
We.
So we don't need to
It's not that simple, because okay, even if you saw them, like the vertex in, remember like you could have like okay, say like let me draw something like very weird. Okay, and then let's say. So all these vertex you need to consider, right? This is the leftmost one. But those vertex actually are not intersect with this line at all. Okay, so what I want to tell you is that sorting doesn't solve this problem completely. Okay, not completely, but yes, I mean, in the following, I'm going to talk about an algorithm that is able to do this triangulation in n log n amount of time. But it's not through sorting. Okay? Does that answer your question?
why is it not complete?
First, like you need to make sure this line does not intersect with any other segment, right? So that comparison like take a linear amount of time, right? Is there any question here? This has nothing to do with the location of the vertices, right? Yeah. Okay, I think if you still have question, we can talk about this offline. Okay. Okay. Yeah. Let's. I mean, we're running out of time. Okay. So anyway, so that's okay. Think about this. Okay. We want to be able to triangulate this simple polygon faster than n squared. Okay, so first thing that came to our mind is that okay, if we are able to, because we are able to do the convex polygon very quickly, right? Remember, for convex polygon, because you just need to introduce the diagonal. And you are done, right? From a given vertex, and then you are done, right? Remember, I mean, at the beginning, I draw something like this, right? Right? You just arbitrarily pick one vertex, and then you draw these diagonals. So this thing can be accomplished in linear amount of time. So which is great. Okay, you cannot. Do any better than this, okay, really. So, yeah. Obviously, simple polygon is not the convex polygon, okay? So the next thing that we may have in mind is that is it possible to divide the simple polygon into several convex polygons? Okay, and then triangulate each of them. Okay, so it's like you know, kind of like a divide and conquer. Okay, try to divide them into convex polygon and then deal with each of them separately.